In this video, we're just going to spend some time doing a couple more examples that will illustrate the concept of a span of vectors, right? So just a couple examples to see how this concept relates to a lot of our previous work. So let's say our first example. So let S be the set of these vectors. So 2, -1, 1. And 1, 0, -1, right? And then here is what we're asked to do. Describe all vectors in R3 that are in the span of S, right? So we need to describe all the vectors in R3 that can be generated by all linear combinations, or I should say a linear combination of these two vectors, right? Well, how can we possibly do that? You know, there are infinitely many vectors in R3, right? Well, what we can do is we can actually translate this question into another question that relates to linear systems. So let A, B, C be our vector in R3. Now obviously this represents all possible vectors in R3, right? So in order for us to describe these vectors that are in the span of these two, right? The question would be something like this. What must be true about these three components in our vector? So what must be true about A, B, and C if, again, this vector, so if the vector A, B, C is in the span of these two vectors, so the span of S. Right? Well, let's set up our system. Right, so let's set up a linear system, but this one is different in the sense that I'm not going to have a specific target vector, right? What we want to describe is, okay, what must be true about this vector if it is in the span of these two? Right, so let's set up our columns 2, -1, 1, 1, 0, -1. And now we have kind of the, the generic set of constants on this side, right? And what we need to do is to put this in an echelon form and see what would have to happen to avoid any contradictions, right? Because again, if we avoid contradictions in this particular system, then it means the vector A, B, C would always be in the span. So if this system is always consistent, right, then we know that the vector A, B, C will be in the span of these two vectors, right? So let's go through the process, and it might look familiar to you, right? But we're going to swap our third and first rows. Then I get my 1, -1, and then my C is now up here, and then -1, 0, B is still in the middle, and then 2, 1B, 2, 1A makes up my third row. So again, let's eliminate the -1 and the +2. So R1 plus R2, -2 R1 plus R3. Right, so now we'll have 1, -1, C. Then when I add the first row to the second row, I will have 0, -1, and then b plus c. And then if I take negative 2 times the first row, add it to the third row, I'll have 0, 3, and then a minus 2c. So let's write it as a minus 2c. And then let's go ahead and eliminate this. So if I do, so we can, technically we could do it without making this a pivot, but let's go ahead and make it a pivot anyway. So if we take negative row 2, that produces 1, negative 1, c, 0, negative 1, b plus c, and then 0, 3, a minus 2c. And then now let's eliminate the 3. So, actually, why did I wrote down the exact same thing? So these would now be negative. So all those coefficients are now negative. So there and there. There we go. And then let's do negative 3 times row 2 added to row 3. Alright, so we'll have our 1, 0, 0 there. Then we'll have our negative 1, 1, 0. Then we'll have our c, negative b minus c. And now take negative 3 times this, and then add it to this. So I'm going to have a, and then a positive 3b, and then plus c. Right? And there we go. So we know now for this system to be consistent, then a plus 3b plus c must be equal to 0. Right? So for this system to be consistent, a plus 3b plus c must be equal to 0. That means I can now describe the span of S completely. So let's see if we can write this down using our set builder notation. So this implies that the span of these two vectors, 2, negative 1, 1, 1, 0, negative 1, is equal to the set of all vectors in R3, A, B, C, with the condition now that the first component plus 3 times the second component plus the third component must be equal to 0. So they can be, so A, B, and C are constants, but they have to satisfy this equation, right? And there we go. So now, not only do we have a way of determining if a specific vector is in the span, but we can actually now describe all the vectors that are in the span of these two. So if the components of my vector don't satisfy this condition, then this system won't be consistent, and therefore that vector won't be in the span, right? So it's really just showing how, again, we can slowly inch towards this more general statement about what the span is. So not really focusing on specific vectors, but describing all the ones that are possible. All right. So that's our first example. Second example is something that we haven't done in a while, but let's revisit the concept of homogeneous systems. So let's consider this system. So it's x1 plus x2, and let's say minus 4x3, and then minus 4x4 is equal to 0. And then let's say x1 plus 4x3 and then plus 3x3 is equal to 0, right? So we have our homogeneous system. Let's go ahead and solve this system, right? Well, if it helps, it looks like it is in echelon form, but maybe we can put it in reduced row echelon form, right? So let's do this. We got -4, and another -4, and then we got our zeros there, and then 1, 4, 3, and then our placeholders there, right? So again, it's almost in reduced row echelon form. I just need to eliminate this. So let's take the negative of row 2 and add it to row 1. So we will have, so row 2 stays the same. And then I'll still have my pivot there. Then I'll have 0, and then the negative of this, so -8. The negative of this plus that, so -7, and then still 0 there. All right. So when we look at this system, there are 4 variables, right? x1 through x4, but there are only 2 pivots. Right, so we know that the variables that correspond to these 2 columns are free variables. Right, so both of these are free. So we have our parametric form of representing this solution set. Right, so let's do this. So let t be equal to x, or let me say it this way. Let's say x is equal to x4 is equal to t, any real number, and then x3, let's say that's equal to s, any real number, right? So if we're 2 free variables, then let's solve for the remaining 2 variables in terms of our free variables. So the third equation tells me, or I'm sorry, the second equation tells me that x2 is, or x2 plus 4s plus 3t is equal to 0. So therefore, x2 is equal to -4s plus 3t, right? And then the first equation tells me that x1 minus 8s and then minus 7t, that's equal to 0. So therefore, x1 is equal to 8s plus 7t. So let's write down our solution in vector form, right? We have all these different ways we can write it down. So in vector form, here's our solution set. So the solution set is, so it is a vector of the form where x1 is 8s plus 7t, x2 is -4s plus 3t, x3 is s, and x4 is t. But now I can look at this a little bit more closely. So let's do that trick where we separate each of our, in this case, parameters into separate columns. So for instance, the first entry has a 8s, and then a -4s, and then a 1s, and then technically a 0s. There is no s in this fourth component, so there's a 0s there. I don't need to write the s, I'm just going to write it as 0. And then plus, let's now collect all the t's. So we have 7t in the first component, 3t in the second. There is no t in the third, so 0. And then we have a 1t there, right? Then let's factor out the variables. So let's factor out the s. And then we have 8, and then minus 4, and then 1, and 0. And then plus t, and 7, 3, 0, 1. But look at what we have now. This is our solution set. And what we realize is that the solution set is any linear combination of the vectors 8, -4, 1, 0, and 7, 3, 0, 1. Because these are my constants now, right? These are my scalars. They can be any real number, right? So we can actually describe the solution set to our homogeneous system as the span of these two vectors, right? In fact, let's write two things down, right? So the solution set is given by any linear combination of these two vectors. So the 8, -4, 1, 0. Actually, let me write it without the set notation now and just say any linear combination of this vector and this vector, 7, 3, 0, 1, right? But we know that any linear combination of these two, well, that's the span, right? So we can actually say this, right? The solution set, or the solution, is actually the span of these two vectors. So 8, -4, 1, 0, and 7, 3, 0, 1, right? And remember, this whole idea of the parametric solution set is that we have infinitely many solutions, right? In fact, again, this is, we have infinitely many here, right? That's why we need this parametric form. So all these infinitely many solutions can be described by just saying span these two vectors, right? So any linear combination of these two will be one of the infinitely many solutions to this homogeneous system, right? So up to this point, we were pretty proficient at coming up with our parametric solution set, but now we can take it a step further and express that solution set as the span of two specific vectors, right? So again, the solution set is infinite, but our spanning set is finite. So with these two vectors, we're able to generate all these infinitely many vectors, right, that will satisfy our linear system. That just happens to be homogeneous. All right. So with these two examples, it just kind of sheds light again on how important this concept of the span is, and it's a very, very efficient way of describing something generally, to say, okay, with these two vectors, I can generate infinitely many vectors that will have a consistent property, and that property is that they sought their solutions to this homogeneous system. All right. Hopefully you found those two examples interesting and made you think, which is my intent. All right. See you in the next video.